So this video is basically an answer to a question I get occasionally, and it's one I got recently. Somebody had watched a video, I was using a logic probe, and just wanted a little bit more information about them. So I've thrown together a simple little, basically a flashy LED circuit to demonstrate what we use logic probes for, and also other tools. If you can get these in little kits. This is a logic pulsar. And then there's also a little logic analyzer here. Now I have like 4, maybe 5 of these kits. They actually come in a little box here, and they come with a little instruction manual for each. You know, the pulsar, the logic probe, and yeah, they do call it a logic monitor. This one happens to be made by Global Specialties. I think they still make this kit. Don't take my word on that. You'd have to check. I know Global Specialties is still in business, but I'm not 100% sure that they still make this kit. I think they do, though. But I usually can find these things on eBay cheap. I think the last one of these that I got, I think I got for like $5 or $6. I mean, at an auction, somebody had it listed for like $5, $6 start price, and I was the only one that bid on it. Because I think a lot of people don't use them nowadays. Now this little kit, if you get one of these, it comes with some different probe tips. It comes with the shorter tips, so the tips just unscrew out of the end here. And it comes with some longer ones. If I can get one out of the kit there, it's a little longer. It's got little wire clamps that you can stick on there. It's got little grabby jaws. It even has a larger grabber that actually just pushes on to the end of your probe tip there. But in the kind of stuff that I work on, which a lot of it tends to be vintage electronics, these come in very handy. But even for modern radios, let's say, like CB radios and whatnot, these can still be used. They're perfectly suitable for using. Now, one thing I commonly use these for on a very frequent basis is Pll Synthesizer Circuits. If I question whether programming is coming from the channel selector switch, so that's just a rotary wafer switch that supplies either a 0 or a 1 to the input pins on the PLL, and that's what's used to program it so it knows what channel to be on. But that's all it's basically sending is either a ground or a voltage. Well, that's what a logic probe is checking. It's checking for 0s or 1s. A 0 being basically ground potential, 1 being whatever system you're working on, whatever its operating voltage. Normally in this, like in this case here, 5 volts is a logic level 1. But that's what these are used for. Now this, you can make your own. I probably have 1 or 2 that I made back, God, when I was a kid. I used to make them out of you can't fit them inside of a normal ink pen, but if you get those really fat, clicker style ink pens, you can actually shove a circuit inside of one of those. Just, unscrew the top or the bottom, whichever, pull the pen cartridge out, and you can fit a circuit inside of one of those and make your own little logic probe. Now this one has a pulse light, and it also has a memory function, so you're not going to be able to cram all of that into an ink pen, but just a basic high-low circuit using a comparator IC, you can shove that into a fat ink pen body, and works just fine. Now, what's inside of one of these, I've actually, because like I say, I had several of them, I actually dismantled this one. Just 2 screws hold it together on the back side, but that's what's inside of one of these. So yeah, you may think, oh, there's nothing there. Well, actually, there's a fairly complicated little circuit inside this one. And like I say, that's the main reason, is because this has the memory function, so you can plug this into a circuit and walk away. And if you're trying to like capture a glitch and you don't have an oscilloscope or a logic analyzer, well, this little probe here can catch stuff like that. If there's an intermittent glitch on a line that should never go high, let's say, you attach this probe, or if it's high and it's glitching low occasionally, you can just plug this, or attach this to that terminal and just walk away. And if you come back and the pulse LED is lit, that means that it had changed states, and it stores that. But I think this has a 339 in it. Pull the serial number sticker up there. Yeah, LM339. So this has a which is what a quad comparator. But still, it's not super complicated. Then they're very handy. Now, in the example I have set up here, I've got, like I say, a basic flashy LED style circuit set up. And you can see it's scrolling through. Now, actually, I've got that. Actually, there's a pause. Because this IC, what do I got? 8 LEDs here, and this actually has 10 output pins. So at the end of the 8 count, you can see there's actually a pause before it starts back at 1. And that's because I have... What did I do here? Yeah, I've got reset tied to ground. So I would want that attached to output number 9, which should be pin 9, I think. Without... Let's see here. See if that works. Yeah, okay, now it's cycling straight through. Okay, that's better. That way there's not a lag there. I can just eliminate the last 2 output pins. I'll just reset it once it gets to 8. But anyhow, we're going to use the logic probe, we'll use the logic pulsar, and we also use this little logic monitor that they have, just to show what they're used for. So, something like this. Let's say you're tinkering around, and, you know, like I say, these can be used in radios. It doesn't need to be used for building little hobby, flashy light circuits. It can be used for rather advanced stuff. Like I say, I use these with Pll Synthesizer Circuits for checking, you know, input programming to the PLL ICs. Now I have, this LED is attached, so what I have here is a NE555 timer IC set up as a clock source, okay? The output of that is actually, every time this flashes, if you watch, every single time that LED flashes, it will advance 1 up here, because that's how fast it's flashing, the clock pulses. And I can actually change that time. I actually made it adjustable, stuck a trimmer resistor here. And you can see how fast it's scrolling up there. And eventually you get to the point, I turn it up so fast that it looks like the LED's on continuously. It's actually not. It's because it's flashing so fast. Because you can see that's actually how fast it's changing states. The clock is pulsing. But monitoring just the output of this, it's flashing so fast. You reach the point, our eyes and our brains are actually extremely slow. You hit that edge that's known as persistence of vision. If you flash something fast enough, it looks like it's on continuously. So if we turn that back down to its slowest state, and that's just, and that timing state's just set up between it's an RC time constant between that trimmer resistor and an electrolytic capacitor I have there. But if I take the logic probe, so we can just really quick demonstrate, if I attach it to a ground, the ground rail, you can see the low light, or the 0, illuminates. And if I switch over to the supply rail, the voltage supply rail, you can see now the high LED is illuminated. That's basically all it is. It's just a pair of LEDs. You know, you ignore all the other switches on there. Like I say, in its most basic form, a logic probe is just either showing you ground or voltage, 0 or 1. That's basically all it's doing. So if we take the logic probe and attach it over here. Oh, come on. Get on the right pin here. So you can see I have it attached right at the LED, and you can see it flashing back and forth. Every time this is illuminated, it illuminates high. When the LED goes off, it switches to low, because the output of that, the clock output of the NE555 is going low. But you can see that. You know, and if we were troubleshooting something like this circuit, and it's like I say, I just set this up as a good little simple demonstration circuit. So we have a clock source, and then we have this IC is actually it's a TC4017, and I'm using that to drive these LEDs. So you know, it's a functional circuit. So it's, you know, something you could find in a basic little flashy light circuit that you buy, you know, let's say a little project on eBay or, you know, Amazon or something. But that's just a decade counter divider. But let's say we were having a problem. We built our little circuit. We know we have a clock source because, you know, if we stuck an LED here. So, you know, let's say what actually calls a fault. Okay, I'll unplug that. So as you can see, we have a clock source here, but our LEDs aren't changing up here. We know we have a problem. You know, if we were to take our logic probe, let's say we didn't have this LED in here, you know, we could stick our LED here and we could see well, we have output from the clock source, but when we go to the input, now you can see the pulse. Don't pay any attention to that. but as far as high-low states goes, there's nothing there. And we can see, if we go up here to these LEDs, we can see, same thing. We only have one LED illuminated, but all the rest of them are low. For some reason, this is not count. It stopped counting. That's because our clock is missing. Now, we could do something like take our pulsar. Now, the pulsar, digital pulsars, basically, all they are is supplying a voltage. So every single time I touch that button, it'll fire a single little short pulse, or a logic level 1. Now if I hold on these, if I hold this button down for 1 second or longer, it goes into a continuous mode, and it will fire a continuous series of flashes. So if I hold it down long enough, you see the light, and as long as I hold that button down, you can see the LED stays illuminated. So it's sending out a really fast set of pulses. But if we take this now and apply that to the input, now if you watch those LEDs up there as I push this button, you can see every time I push the button, it advances one position because I'm sending out a single pulse. And if I hold it down for 1 second, you can see how fast it's flashing now. And I don't know with the camera and whatnot how that'll show up, but it's actually cycling through really fast. But that's how fast the pulses are coming out of that probe. So, like I say, this is a handy little tool as well. You can go in and use this to supply voltage. If you've got a problem in a circuit, you can take your pulsar probe in there. Once you've tracked down a problem with your logic probe, you can come in with the pulsar and apply a clock source or a single pulse by just individually hitting that button. So, in the case of this one, we could, if we had a problem, we used our logic probe, we found that we had a clock source, we had output here, but we had no input here. We'd eventually find, aha, there's our wire, it's disconnected. Nitwit, you forgot that when you assembled the circuit. Which happens. When you're prototyping, you're going to run into stuff like that. You'll turn a circuit on, and it doesn't work the way it's supposed to. Well, you're going to have to troubleshoot it. Logic probes are really handy for CCL, especially for TTL and CMOS based systems. And that's type of logic ICs are still used to this day. Yes, we have microprocessors. You can cram millions, probably billions of ICs like this into a single chip nowadays, but they're still used in products. I will still see 4074 series ICs used in products that are made today. And if you work on vintage equipment, it's very common to see that kind of stuff. And like I say, it doesn't even need to be those specific series of ICs. Like I say, I use this on PLL ICs at the input. I just need, but the really handy thing, a lot of people are probably thinking, well, Mike, can't you just use a voltmeter? Yes, I've got a voltmeter there, got a voltmeter over there, I've got voltmeters everywhere. The problem is you have to take your eyes up off of the board. This is really fast to use because I can just come down here to the board, pick a pin, and I can see it change state. I never have to take my eyes off of about a 2-inch area. I just stay right there. I can just look at the board. I don't even need to lift my eyes up from where I'm probing. I can see that in my peripheral vision when that light flashes to high, so I can see it's active. Okay. Like I say, just really handy. It's all right here. That's basically all I need to see. And you can see how sensitive it is. Just me touching the probe is illuminating that high. Very sensitive little guys. The logic monitor, now this is basically kind of like this, but it has an LED for every single pin on the IC. And it's actually, I mean, it's complicated, but it's actually a fairly simple little circuit they have in there. They basically, whichever pins are at the lowest and highest state, it sets those as basically the ground and the voltage source to power a bunch of Darlington transistors in here. That's basically all that's in here. It's just a Darlington transistor for every single LED. And when it breaks the threshold, it'll turn that LED on. So if we, now I like to just turn this off for a second while I clip this on. Don't want to go shorting anything out. If we turn that on, we can see it's actually counting. And you'll see it's not in series. Actually, I printed out, where is that? Over here. I printed out the first 2 pages of the data sheet. for a 4017. You can see decade counter divider. But this is something that's really handy to have when you're working on something like this, is to have the data sheet. It tells you the output pins, it'll tell you high-low states, timing, you can see the series, how it counts. In this case, we can see, and it's the reason that, I have these LEDs wired so that they illuminate in series, consecutively or sequentially in series. But if you look at this, you can see that the lights are just, it's bouncing all over the place. That's because we can see, pin number 3 is actually the first. So it actually, when it's, the way this is wired, it actually goes pin 3, 2, 4, 7, 10, let's see, 1, 5, 6, 9, and 11. Because, yeah, 11's number 9. But that's actually the count. But it's really handy. Got the data sheet. You can easily see in what order which pins are firing. And like I say, you can just, if you're having a problem. But this is nice because you can see every single pin. And you can see if I turn the speed up on this, you can see it managed just whipping through there. If we turn that back down to its lowest speed, and we can also see, even something, now I don't have the carry out because I don't need it. I'm only using a single IC here, but if we needed the carry out pin, like pin 12, we can see every time it cycles through a count, it switches states. It goes high, low, high, low. Every time it goes through and cycles, makes one complete cycle, pin 12 changes state. You can see the clock input on pin 14, so that's actually the same LED here is the clock output of our timer circuit that feeds into the 4017 on pin 14, but we can see that there, nice steady beat. But really handy little guy. And early, actually working on CB radios, early PLL synthesized radios did not have a PLL IC. They actually had a little module that in many cases was made up of TTL and CMOS series ICs. They had individual counter divider circuits, just like this actually, and it would divide down your reference oscillator. Every time it would go through, it would divide by 10. You'd have several stages of divide by 10 circuits. But you're working on something like that, well, these are the perfect tools for diagnosing something like that. If you have a problem with one of those circuits, you can just clip this onto the IC and see, is it active? Clip it onto the next one. Even here on this board, this is just like a little project trainer. I like it because it has, dip switches, got some pulse outputs, got all kinds of, actually out of view there, a bunch of data switches, pulse. It's got built-in, several built-in power supplies. It has a 0 to 15 adjustable, a -5, a ground, a 0 to -15, a positive 5 volts, up here and down here, several ground points, got some, 7-segment LEDs, and has these 8-bit display using LEDs, but they're being driven by an IC. I can just take this and clamp it onto one of those. Get it around it. Now, it actually doesn't matter which direction you turn this, hook this up, because like I say, it just picks the highest and lowest pins. But you can see, so each IC is handling 4 of those LEDs, and you can see as the first 4 illuminate, you'll see 4 of the LEDs change up here. And then if we go over to the other one, you can see when the last 8 LEDs are cycling through, you'll see the LEDs change over here. But really quick, you can monitor every single pin on that IC and see if you've got activity. And do you have the activity that you want? So, like I say, they're just time-saving little tools. It's kind of I don't want to say it's a lost art using a logic probe, but I sometimes kind of think that because technology's gotten to the point where you can't get into it, like a microprocessor, you can't get in to probe the individual ICs. Like I say, there could be thousands, millions, hundreds of millions of components actually housed in one little IC now. Well, not so little, but big microprocessor ICs. It's just amazing how much stuff's in there. But these probes still have a place even in today. Like I say, occasionally you'll see products that have a microprocessor, but they'll still be using TTL or CMOS style ICs, just because and that's why they're still produced. They're so widely used in the industry. They're handy little ICs. You'll occasionally see maybe somebody designed a circuit, using a microprocessor, but they need to do some level shifting, or they need to do some, divide down or count a circuit, and they forgot to add something into a circuit. They can just plop a TTL or a CMOS IC in the circuit. They're cheap, readily available, and their problem's solved. So, and when you're starting learning electronics, trust me, you're going to spend a lot of time playing with CMOS and TTL ICs. So, you can go online, buy these things. You can buy them from China. You can get Chinese-made ones. Honestly, they're probably just fine. There's, like I say, the basic logic probe is nothing but two LEDs, a high and a low. If you get the little bit more advanced ones, they'll have a memory function. You can also set these for different sensing states, because this will sense and also depends on the speed. It's kind of like this. The speed at which that pulses is actually determined by if I put this in CMOS or TTL. And same thing with this, has TTL or DTL and CMOS positions, but you can make one even. Like, just go online. I'm not going to go into making a logic probe, but like I say, it's nothing but a comparator circuit. And there's plenty of people that have schematics and diagrams, how to make them online. There's probably actually even here on YouTube, there's probably videos of how to do that. But I think it's the long forgotten tool. Yeah, a lot of people just, and every time I seem to use one of these, I'll get a bunch of questions about it. Mike, you got a logic probe? What the heck are you using that for? I thought those things were extinct. No, they're still usable, people. They've got lots of use. And like I say, in the case of this one, I think they still make, and actually let me grab one of the other kits. That one's actually missing the sticker on the top. There it is. I got a pile of these things. It's actually Logic Analyzer Kit LTC2 is this kit. Like I said, I think they still make this. I'd have to look it up online. This is actually the kit that I'd taken the other probe that I had dismantled over there for you to look at. But same thing, got the logic monitor, the pulsar, and then the dismantled probe here. But yeah, handy little kits. So if you're going to be working with, especially with CMOS and TTL ICs, get yourself one of these. If you work on stuff that has Pll synthesizer circuits in it, like CB radios, these are actually handy for checking to see if you have channel selector problems. If you're having program, you've got a broken connection between, which is very common in CB radios, especially if they've been worked on a lot, and they have those flat flex cables that connect between the channel selector output and the input, or the programming input, to the PLL IC. Those flat flex cables, if they get bent one too many times, the traces start to break. Very easy to diagnose with one of these. You just touch one end, see it high, touch the other end. If you don't have the high at the other end of that cable, well, you've just found the problem. And it's very simple to just go down through a PLL IC. You can just touch it to a lead, spin the channel selector around and see if you have activity on that pin, and just go from input pin to input pin. And if you have the service manual, you should have the truth table. Okay, the truth table is going to tell you which pin will be high or low, every pin, depending on what channel it is. So you could stick it on, let's say, channel 12, look at your truth table, and it'll tell you maybe high, high, low, low, high, low, and you can just go through with your logic probe and go high, high, low, low, high, low, or whatever it is. Like I say, very, very handy, because it keeps your point of view in a very small space. You don't have to look over to a multimeter and then look back down at the circuit, go to the next one, look back over to multimeter, back down to the circuit. I think you can probably even find these. I think I've seen, don't take my word on it, but I'm pretty sure I've seen some of these even have a little speaker in them. Personally, I don't know why you'd want a speaker. I've got eyeballs. Obviously, if I can see to put that tiny little tip down onto a trace, I don't need the audio part. But like I say, if you don't have one, make one. And you don't even need to put it in a housing. You can just make your own little logic probe and stick it on a piece of proto board like this. Doesn't need to be anything fancy. You can get these little proto boards. Like this board here is made up of what? 1, 2, 3, 4. There's actually 4 sections. There's 2 little strips down here, and I've got them jumpered together, and then 2 bigger sections up here. But you can just buy yourself a little piece, one of these little small proto boards, put a little logic analyzer circuit on there, and just use it on the board, and then just have wires run down to it for your hot and your ground, and then have another wire that comes off for the probe tip. Now, be aware that if you get high in frequency, it does get to a point, you'll see there's actually a jack in the front of this. Now, it's using the ground here for the ground inside of this probe. But once you get up to, with one of these things, probably over like a megahertz, it's a good idea usually to hook up an external ground or a separate ground here to keep your ground length as short as possible. Having these really long wires, once you start to get up in frequency, you'll start to get intermittent problems or readings with your probe. So once you get up into the megahertz range, yeah, you definitely want to have the ground lead here to try and keep your lead length as short as possible. But for normal stuff like this, that's flashing, even at the highest rate here, that's actually very slow in the grand scheme of things. May seem really fast up there, but yeah, honestly, that's really, really slow. If I can still see the LEDs flashing, yeah, that's slow. Because like I say, our brains and eyes aren't that great. You reach that persistence of vision, and that LED right there proves it. You can see flashy lights up there, but when you combine all of those into one LED, you can't even tell that thing's flashing anymore. And like I say, the logic probe's really handy for diagnosing problems like this. So I'll just cut it off there. Like I say, I wanted to make a really quick video to try and explain why I still use these. And if you get these little kits, like I say, they show up. There's usually a couple of them for sale on eBay at any given time. I'm sure they'll disappear now. But if you keep an eye out, save a search or something. Just keep an eye out for when these things come up for auction. A lot of times you can get them really cheap. Like I said, I think the last one I got was like $5 or $6 for the whole kit. This thing alone cost more than $5 or $6, and so did this, and so did this, and with the nice little kit with all the accessories. That's cheap as dirt. So there you go. Logic probes and why we still use them and why they still have a place in our modern life.